Okay, back to diodes. All right, different types of diodes. Different types of diodes. Sure, we'll go with that. Different types. All right, we've got the LED, which stands for light emitting diode. Let's see. Oh, I better put this. Photons are released when the electrons meet holes in the junction. You maybe don't have to understand that so much. So, photons are released when the electrons meet holes in the junction. And of course, depending on the material, different colors are produced. Different colors can be produced. I am currently thinking about putting LEDs in my airplane. They are stupid expensive.
$500-ish?
Oh, just the basic LED is just under $400 now, so they've come down in price. But the nice ones where you can wire them to wigwag, they're like $1,000 each.
You know, just kind of.
Didn't we talk about just using the ones from the classroom?
I know, just you guys are going to wire
Just
them
get
all
a
up in
bunch
there
of
for
them.
me.
So, do you have to modify your type certification on that one?
No, STC, which I guess would be yes. I'm modifying that. Voltage drop will be different for each color.
Would the LEDs be in your center, like in the console, or are you talking about like wing lights and everything? All lights?
Landing and taxi.
Landing lights?
Landing and taxi.
And with that, does that mean you would have to replace them as frequently as you would like a bulb?
That would be for sure because the 4509 GE 4509s that it take don't last very long.
Are they halogens or?
No, they're incandescent.
Ah.
Let's see. We got the LED. We have the laser diodes. You just have to do that because laser. No, because I always do it. Laser similar to an LED. Similar. Similar to an LED. Where would I find a laser diode? In an obsolete thing that you may not even know what it is. Optical storage drive.
What?
DVD.
What? You don't have one of those?
Storage drive.
Yeah, I didn't realize how.
Yeah, CD player.
Like a CD player. Okay, now I have to explain what a CD player is. So I don't know.
Or no, hard disk drive is just.
Wow, I got to update my notes here. Photodiodes. Photodiodes. More or less. So I'll just write my notes as the N to P, or the NP junction is designed to sense light. To sense light. When light reaches the material, DC voltage is produced. And what would that be found in?
Oh,
So,
Like solar panels.
Well, couldn't it be in a cell phone too? Like when you put out in the sunlight and its phone brightness goes down? and shit?
Light sensors.
Oh, so that's what the light sensors are.
There we go. Yeah.
Oh.
Okay, I probably could have leave these out of those last few out of my notes. Maybe next time. The laser and the photo diode because it's not relevant. But we'll get back to what's relevant. The Schottky diode. Oops, I already misspelled it. Schottky. Schottky. That's kind of how you would say it. Diode. All right, have a lower voltage drop, more efficient and faster switching speeds. So have a lower voltage drop. Lower voltage drop. More efficient. And faster. But, and trust me, you don't want this, disadvantage is this diode has a larger reverse leakage. There were those potato chips they made for many years that had the warning on the bag that it caused large reverse leakage.
Low-fat Pringles.
It's what?
Low-fat Pringles.
Is that, yeah, with the Olean or some stuff like that. Yeah. Yeah, you don't want reverse leakage. What? So, don't tell me. In reference to a diode, what is reverse leakage?
Voltage going through it when it's supposed to be getting stopped.
Yeah, voltage going through it backwards, or now we can use the proper terminology in the
Reverse bias.
reverse bias. So it would actually transfer through in reverse bias. We don't want that. And then the Zener diode.
A Zener Princess Warrior diode?
Yes.
Fuck yeah, sexy.
He dresses up like that at night.
Works like, I'll say normal diode in forward bias. So forward bias is going to turn on. It's fine. Works like it normally would. But also permits flow. That's so funny. Also permits flow in reverse bias, which then that would just be called a wire. But it's not.
That's not very good.
So
diode.
there's more to it. So permits in the reverse when it reaches a certain threshold. So. Also permits current to flow. In reverse bias.
So it's just a wire.
That's what I just said. So it's a wire. But it's an expensive wire. Reverse bias when the voltage is above a certain value.
Wire plus.
Wire 2.0.
Why is it so good? Why did we make the wire 2?
Value. This is known as
Do
the
you have an example of a Zener diode actually used?
not right at the moment.
Electronic systems trader, voltage regulator thing. Have one.
No, as the breakdown voltage.
So don't normal diodes also have a breakdown voltage, it's just different than the xenon?
Yeah, okay, but that means it's broken at that point.
Okay.
You've blown it up. So
This is-
you know,
this is a
so yes,
fundamental-
every diode is a Zener diode once, if you try hard enough.
Copy that.
So a regular diode, if you put enough voltage in the reverse bias, it will blow through it and call the breakdown, and then it flows current just fine. The Zener diode is meant so that it will actually heal
Do it
itself.
once more again.
Yes, you can do it over and over. So an example of something like this would be, you could use it in a voltage regulator. When a voltage reaches a certain point, then it's going to have a breakdown, and it will send the voltage then to ground, or something similar to that. So that's where I've seen them in some of our examples. All right, we good with all that? Let me see, I have considerations, things to think about. Which is kind of funny what I'm going to say here, because it's like, what? No. Even I'm looking at it going, well, that's not always true. So diodes get hot and are often let's take a minute or two, and are often attached to heat sinks. All right, what's wrong with that whole sentence? Not the spelling and the grammar, but
Heat sinks part.
your verb came up now.
Punctuation is
What's the advantage of using LED
They-
lights?
They're not hot.
They're not hot.
Yeah, I was gonna say, but is it a difference between like an LED diode not getting super hot, or is it like they're super sensitive?
It's just something I hadn't thought about till I looked at it. I was about to write it, and I thought, okay, well, I got a problem with this whole thing, so let's just write it and talk about it.
LEDs
So-
do get hot.
in the
So-
AC alternator. are
There you
attached to a
go.
Yeah.
Say that again.
The diodes in the or the DC alternator are attached to a heat sink to keep them cool.
You can call
Right.
it an AC.
Yeah, and then
alternator.
larger LED lights have a massive heat sink. If you have it running, don't touch the back of it. It will get
Thank
really
you.
hot.
Okay, and then let me think about. So we do have a pretty massive LED light in the black room, and it does have huge heat sinks to it.
It gets cooking.
Okay, so thank you for that.
That's why your landing lights are so expensive. You're paying $5 for the LED and $395 for the heat sink.
Yes.
Probably. So is it kind of like, it seems like like you think about an LED bulb. and
I
it's
know.
like nearly as hot as a.
Nope, not nearly as hot as
so
a
is it a
incandescent.
relative heat thing? Is it like saying that it's gonna pop at a
They
much
don't
lower heat?
degrade with heat quite like an incandescent would because of the draw of current.
Okay, so let's maybe back up a little bit. We're talking about this. Some people are going, I don't know, what's a heat sink? So a heat sink is not something you wash your hands in. A heat sink is something that absorbs the heat and gives it back out somewhere else. So like we talk about the alternators with the 6 diodes, they get hot. And so they're attached to a plate of metal, aluminum, which has good transfer of heat. And that is usually attached somehow to fins on the back of the alternator so that the heat goes through that out into the fins and gets air cooled. So a heat sink is something that draws the heat away from what you're trying to keep cool. Like in computers, I've taken enough computers apart. That is it processor?
GPU.
CPU.
CPU.
CPU has, you pop it out, it's got like white lithium grease, but it's not white lithium. It's a heat sink compound.
Yeah.
Yeah, thermal paste that's made to conduct the heat away from that processor to a plate that has fins where the fan is blowing on it. So that's the heat sink. And if we thought about cylinders, I don't have it in here anymore, but cylinders on an aircraft have cooling fins on them. That's just another way of a heat sink. Right. They get hot. Well, they are used as rectifiers. We already talked about that. And we already talked about, I don't know, rectifiers allow AC voltage to easily be converted to DC. And I think we've really talked about that quite a bit, haven't we? Nobody's answering me. So I believe we have discussed this many times. And what are we looking at here?
Wheatstone Bridge.
Actually, you're very close. It's not a Wheatstone bridge because a Wheatstone bridge has to have a
Resistors.
something in the middle,
Yeah,
an equalizing circuit. Otherwise, it's just, I don't know, it could be drawn in a square or a circle, but this represents a
Full-way rectifier.
full array rectifier. All right, everybody knows how that works, and we're okay with that?
Can we go
Alright.
over it a tiny bit?
Yeah, thank you. Okay. So, well, I guess we can go to a pen. We can just remember a few things. We have a diode. I just student call them doids. I don't know why. Which way? Let me see. Which way is positive? Over here? Over here. To make it forward bias. This side is. To the left is.
Yeah, where's your
I said to the left side.
Left side would be
Of what?
positive.
Of the diode that I just drew.
Positive.
The red thing. This is a diode. Okay, laser pointer. Can you see that?
Left side would be positive.
I'm just worried Swan is going to be like a cat and start batting my thing. Laser pointer. All right, so right here, which side is this?
Positive.
Positive.
These were thinking conventional.
And then the other side is? Negative. Okay, that makes it what? Bias. Forward bias. Okay, well, with the help of these arrows, I can see that this is a negative. So we're going to be using conventional or electron theory flows. We think this through.
Electron flow.
Electron flow. I will use the laser pointer. So negative comes up here and it gets to this point right here. This would, if this is the negative, that makes it
positive?
reverse bias. So negative turns it on here, yeah?
Yeah.
Okay, so negative turns it on. It comes up to this point. And now this is still negative, so that
Can't go.
doesn't work. So it comes through here, goes through here, and now we are,
Negative.
now we're on the positive side. So we come through and get to this point, we're looking for the positive. That is a negative and that is a negative. So it no longer works. Okay, when we get to this point, we have to think of more positive versus less positive, or more negative versus less negative. So the difference across B to A was basically our full-blown negative, no voltage drop whatsoever. So a little bit of voltage drop. So this is very negative. And this right here, coming across here, this side is more positive. So
Jump from B to D.
yeah, so we'll go through B to D. Let me see if I can explain a little bit more. Yeah, this side is more positive. More because you will have a voltage drop across that. So more positive, less positive. If we were going to put across this diode right here, if we were going to put our Simpson meter across there, which side would be the positive lead, the D or the B?
D.
D would be the positive to our voltmeter, and B would be our negative to the voltmeter, so that makes B kind of a more negative side, and this the more positive side over there. So if we're coming through, even though this says positive right there, we're thinking, okay, I'm positive. When I get to here, thinking, well, how does it it makes no sense. But remember, this up here is the positive side. This is the negative side when we take a snapshot of just that diode. You follow? All right, so then it is, in fact, forward bias. It's going to flow through there and down. And I guess we could do the same thing with A and B. If we're going to look at that first diode, or this diode here, why doesn't it go back up to A? We could look at that and say, well, which side is the negative side? Where would we put our Simpson meter black lead, on the A or the B?
A.
A. Well, then by default, this would be the positive side. So now we can see when it came to A, this is the negative side, that is the positive side, that is then reverse bias, so it's off.
So why doesn't a diode work if you just like put it straight across a battery in reverse way? Why wouldn't it say like, oh, okay, well that's more negative and more positive, and just jump over? Does
Because-
it? Or does it work that way?
No.
Yeah, so I'm just kind of, it seems like, oh, in this case it's like, well, it's more positive, but actually the diode is reversed.
Because there really is voltage running through there, and one side really is is a positive bias, and the other side really is a negative bias.
Would it also be kind of an appropriate way to think of, so like, opposites attract and similars will
Repel?
Maybe
Repel.
if it works for you,
So, like,
I
at
don't
the
see why
A-
not.
At the B point,
B
there's
point.
already electrons flowing through the A point. It doesn't want to continue flowing through that way, maybe, and there's nothing over at the.
Oh, so you're saying this is the negative? No, because opposites would attract, and this
Okay.
is. Yeah, I don't know. If it works for you, I'm fine with that. All right, so we see how that worked. So now, when our voltage source swings the other way, and we're after the top being negative and the bottom being positive in both of them to make it DC. If it didn't do that, then it wouldn't be DC. So now we have the negative going up this way. It comes to this point right here, and it has no choice because that is clearly a positive. This side right here is the negative, so that's going to turn it on. It's going to get to this point
Go right.
and go right because that's what the arrow says, because this is negative right here. We're going to run into the same thing where this is the negative and this is the positive. You can see that. This is straight positive. This is almost full negative, and that would be reverse bias. So through here, down here, gets to this point, and now we're back to where we were before, but it's the opposite. So we are positive, yes, but not as positive as A. So we would get a slight voltage drop across diode 4 if we were to put a voltmeter across there. And if we put the red lead on B and the black lead on A, we would get a little bit of a voltage drop. If we had the Simpson meter, if we swapped it the other way, the needle would go backwards. So that's how we know that this would be the negative, this would be the positive, and through in that way. Got it?
Yeah.
When you get to a certain point, it's a little hard to go, oh, which way is it going? And, thankfully they put the arrows right on there, so I don't screw it up.
It's easier to think about it since if it's alternating, you just follow positive, just follow electron or conventional theory. To go back to that, you just follow conventional theory on the left-hand side.
Yeah?
Since it's alternating, if you drew the arrows backwards, it would, you would go, from there, right, up, down, because it can't go up.
Right?
Then to the right.
Yep.
Up across.
Yep.
Up there.
Yep. But then now
Oh
you
yeah,
can.
yeah. Never mind. Shit.
I know. You're always going to get to a spot where you're like, it goes both ways. Yeah, I've been there, done that. Okay. Let's see. Transistors. Now let's talk about transistors. Transistors. All right. So to understand a transistor, it's important that you understood how a diode works. And we'll kind of go back and just take a quick look at this up here because it worked for me. All right, how these work. So we have a P-type junction, or P-type and the N-type, right? And in order for it to flow, the P needs a positive and the N needs a negative. All right, so that makes it really easy. So the P needs a positive and the N needs a negative. And when you do that, it is in the on position. And if you were to reverse that, it'll turn itself off. And hopefully you remember kind of why that is from yesterday. So in this particular spot right here, we have that negative comes over to here. Sometimes I hate it when they do it reverse current. Positive is going over here, so we have the positive. So negative over here, negative. And opposites are going to repel. So this is repelling electrons this way. It's pushing them out, pushing them out, pushing them out. When it gets to the depletion zone, there's enough force to push it across and start flowing across that depletion zone into the holes, if you will, and going through the holes until it gets to the other side, where right over here, the electrons are then attracted to the positive and through. Down here, even without a battery, what happens is there's enough electrons on one side that are just attracted just enough across the border to fill a hole. But once they get kind of over here in this area, not so much, they're going to stick around home. That's too far to go. And so we just get this area where we have a small area where the electrons crossed over, filled the holes. So now we have no holes on this side and no electrons on this side. So you get an area that is not working, right? But if we hooked a battery up to it, then it's going to suck them all that way, and then it's really going to be off. So it's super off. Got it?
Remember the four-handed smilers.
Yeah. How well did you sleep with that one, huh?
I'm never gonna forget what a diode is.
Who's on first?
All right, transistors.
Halloween too.
Transistors. Two types. Two types. We have the NPN and the NPN. What's that? All right, so we have the base, and really it is all about the base. The emitter, and the emitter is going to have an arrow on it. And that arrow is not pointed in the collector. So the NPN. Which is not pointed in. NPN.
Is that actually what it essentially means, or is that just a...
Just to help you remember which way the arrow goes. So it's kind of like this. The collector is an N material, the base is a P material, and the emitter is an N material. That's the NPN. Base is P-type. Collector and emitter are N. Or the N type. And then we've got the other type, which is P and P. I don't have a thing for that. Put it in, pal. I don't know.
Arrow.
It's just pointed in. All right, so that is going to look like this. There. So we got the base, the collector, and the emitter. And that points in. And the collector is going to be what? P or N? P, the base is, and emitter is P. Now I don't have to write it because I just do that. So point it in. They are used as the little vid just showed us, transistor. Why did I write that? Can be used. I'll put can be used as a switch. Used.
What would they be used as a switch? What would they be used in?
Oh, all kinds of everythings. I mean, solid state. This is like
Is it basically just
So like, Everything electronic.
Yeah, but I mean, I want to like know like a specific example way I can think about it.
Switch
Shut the-
or solenoid.
No, I mean, I want to.
Hang
I'm gonna
on.
be like fucking with these. Like, I mean, is this something that like,
Just use 2 words that you just
or is it just like how a component might work? Like a radio or something.
Hang on a second.
Give me something. Okay, tell me more.
Switch or a solenoid. Can be used as a switch or a solenoid. Why don't I have figure 6 to? I have a figure here. Oh, you should see this figure. Let me see. Did I put this figure here? Oh, I forgot. I got these. Let me see. There we go. Not pointed in and pointed in. Pointy in, pointy. That's what I came up with. I don't know. Pointed in, pointy. All right. Let me see. There we go. Solenoid analogy of a switching transistor. So I just said it can work like a switch or a relay. So this actually is working kind of the same way. So in order to control this lamp right here, I would close the circuit right here, which if we take a look at this right here, is that an NPN or a PNP?
That's a PNP.
PNP. So let's play with that a little bit. So it's pointed in, pointy. So pointed in, pointy. So what does the base need to turn on? So we want to make this a forward bias thing. So the base needs to be,
Grounded.
base needs
A negative.
a negative. Okay, so just look at this over here, right here, my solenoid. So if I close this switch B, which represents the base, what did I supply to this this coil right here?
A ground.
Negative. So it's doing the same thing. Now, keep in mind, I think it's helpful. Emitter and collector can be a little confusing because especially if we look at it in light of what we have off to the left here. And if we remember, the diode was kind of written in more of a conventional theory. Well, if we think about it in conventional theory, the oh, that's what it was. The emitter, yeah, it gets all screwy. The emitter and the collector. I'll circle back around. I think I have a thing to do that with. So anyway, so we have the emitter to base has to be forward biased. All right, I'm going to change something here. When you're dealing with transistors, I may have jumped ahead just a little bit too much. There's an easy way to think about this because it is on the test, the FA test. When it's on, you know, what is forward bias? What is reverse bias? I'm trying to think. I've got it written down somewhere, and it's just like, let me see. I think I even pulled that out of my notes, but I had it written how, like the books would write it. You know, in order for this to work, the emitter to base junction must be forward bias, but the base to collector is reverse bias. But when it's on, it gets really confusing. But if you just take a transistor like this and turn it into 2 diodes, and is anybody in here electrical engineer? Good, because I had an electrical engineer here one time, and he's like, it doesn't work that way. I'm like, yeah, but it made so much sense. So we just take this right here, and we make 2 diodes. So diode 1, we think we want to make it forward bias. So that would be down here, be the negative, right? So the negative side goes there. So we're just going to make it like this. So we got the negative, right, going to the base. Follow so far? Because that's kind of what we did. And then we have this go. So what happens is through here, I'll turn back this on. So we close this. We created a positive coming down through here, through a negative. We close this, comes down through the positive, through the base negative. That works, right? So this is now on. And when this is on, then this is going to flow.
Oh yeah.
Similar to what happened here. That's what it is. So then the emitter to collector, this has to be the P and this has to be like the N. So I don't want to screw that up and say which way is biased. But if you look at it that way, it makes perfect sense to me. How we just add in another diode. So if we add in another diode down here, which way is that diode going? Then this has to be, then it has to look like, kind of like, let me think. Positive is flowing this way, right?
Yeah.
You follow what I just did there? So this is the P, that's an N. It turns that on, and then current will flow
Out.
this way, and out.
So
Using
it's like your
conventional.
base is your coil.
That's what we're looking at here. Base is the coil. That's the controller.
Just like that video.
Just like the video. It gets a little cooler than that. Like if we added a resistor in here, then that would, unlike the analog to the left over here, if we added a resistor here, it doesn't make this less on, right?
On or off.
This is an on or an off. This is binary, right? Ones and zeros. But if we added a resistor over here on the base, then it's not as on. And if it's not as on, then we can kind of control what's going through here, which is where we got in that amplifier circuit. So I'll kind of get into that. But
And so that's why we use transistors instead of.
well, they're faster, they're smaller, they're no moving parts, they're
And you can put a resistor in it and make it.
you can do all kinds of stuff. Yeah, and I'm going to show you some stuff here. We're going to use that. Can be a switch or solenoid. Let me see. What do I got here? All right, we got the nomenclature, which I kind of already did, but we'll just do it anyway. So the base. This is the controlling circuit. That's the controlling circuit. We've got the emitter. The emitter. Using the drawing we just looked at, which was a PNP, so the emitter,
The emitter is the emitter.
yeah,
Emitter.
emits electrons into the core of the diode, where electrons either let me see, either flow into and then out of the base, or flow into the collector and out. So the emitter emits electrons into the core or into the base, where either is going to flow through the base and out, which was the controlling circuit, or into the base and then back up and then out the collector, which the collector is the out and the emitter is the in. Thank you for that. Let's see. Oh, there it is. Okay. This is the fun stuff. Not so much. Connections. Transistor must be properly connected. Then I think I shouldn't have to write that, but then again, I did have to interrupt you to tell you to put a wrench on bolts today, so you never know. So emitter to base junction is forward biased. Emitter to base junction is forward bias. I'm going to go back to this and say the emitter to base junction is forward biased. Forward biased. This is a PNP. This side is, the emitter is positive, and the base is negative. And down here I drew a, I don't like that one. Oh, it's not going to give me a pretty circle. So we got the emitter to the base.
Not be a perfect circle.
That's what I just said. It won't do it on this program. It has to be forward bias. So which way's in? Here's the negative. There's the diode right there. Right? Is that forward bias? Positive and negative. Emitter to base is what? Forward bias. Okay. Emitter to base is forward junction is forward bias. Let's see. In an NPN, so an NPN type, in an NPN, base is what? Base is positive. Emitter is negative. In a PNP, base is negative. Emitter is positive. Emitter is positive. Oh, right here. It's everywhere. There it is. Whoosh.
I didn't realize we're in a different program.
I was in PowerPoint there. All right, so here's my emitter. Here's my base. Let's make it a PNP over here. Well, NPN. We can do NPN. So NPN, this diode right here, which is not really a diode, but you follow what I'm doing here. Just make it easy. And this is an NPN. NPN. Then which one is negative?
The emitter.
Emitter. So that's my negative. So it's going to look like that with a diode. Okay. And if it was a PNP,
Then it would be the other way around.
PNP would be the other way around. This right here would be the other way around. So it'd be this way and that way.
So it doesn't matter what side the emitter is on?
Well, it's the emitter to base. I could have drew it the other way. I could have put the E over here.
Okay.
So no, it doesn't matter. I mean, you know, the emitter doesn't always have to be on the east side of the world, if that's what you mean.
Okay.
So emitter to base has to be on them all. Any one of them. Emitter to base has to be what biased? Forward biased. Okay. That's all. Just forward bias. When you're looking at it, now you know how to turn it on. All right. What else do I got here? All right. The base to collector. Base to collector junction is reverse biased. And that gets kind of weird. So if we look at this up here, we'll just go back with it being an NPN. Let's see, we'll get rid of this right here. There, so back to an NPN. Let's fix this right here. Nobody will know the difference. So good as new. All right, in an NPN, it has to be, that means that emitter is what? N or P? N. Base is P, then this is N. Okay. So base to collector junction is reversed bias. So if I have to put a diode in here, what is reverse bias? Backwards. So would it look like this would be the positive side, put the negative, and then that going that way and that going that way? Okay. Does that make sense? Base to collector junction is reverse biased. That is, in an NPN, the collector is more positive. Oops, that didn't work out. This is more positive than the base. So more positive than the base. Well, the base was definitely negative. Oh, I'm sorry. This is an NPN. So let me see. Go back. In a the NPN. I'm sorry. Yeah, NPN. NPN. The NPN collector is more. The collector is more positive than the base. NPN. This is more positive. More plus than that thing.
How can that be more plus?
Well, I'm glad you asked. Let's see here. If we look at this one, the problem with this one is that it is a PNP. I need a good diagram with an NPN. Let me see if I can come up with an example on that one. We move down one line here. Is reverse bias. Let me see. So let's do PNP. PNP, the collector is negative in respect to base. So in a PNP, collector is negative in respect to the base. Does that sentence hold water there? And a PNP collector is negative in respect to base. Let's see that. In a PNP, the collector is negative in respect to the base.
Sounds right.
I don't know.
Yeah.
Oh, that's the opposite one.
You have the ground there.
Man, this shit's
This one's like, what? All right, I'm trying to figure out how to help you.
We said that was PNP, right?
This one is PNP. It's pointed in. So it's PNP. Pointed
the
in.
base would be more negative.
Pointing.
Positive
Yeah, so how would be
to the base?
yeah.
That's what I was gonna say.
How would it be
That
the
would-
positive collector be more negative than negative base?
Yeah, look
Oh,
on the other
wait a
side of the lamp. It's like negative.
Hang on.
Positive.
Hang
You
on.
said this week was gonna be easy.
No, it is.
Easy for him.
Yeah, that's
I forgot.
Easy for him to watch us fail. Not failing.
I do have my examples. Consider the two resistor diagram, which is diagram F. Do not think of voltage as an absolute. Point B is negative in respect to A. Oh, I remember. That's what it was. Okay. I did okay until I got ahead of you just a little bit. So let's back up just a little bit, make sure we're on the same page. We've all got this, right? Right up to point 2. Emitter to base junctions forward bias, correct? Everybody's good with that. Emitter to base junction is forward bias.
I have a question about that.
Yes.
Emitter debate. So, in the drawing though, isn't that the diode you drew? Isn't that showing reverse bias? That one,
Did I?
like right there.
I might have reversed
That
it.
is that
No.
emitter to junction. Is that
No, this is positive down here. So the collector, forward bias. Emitter to base junction is forward bias. Is the emitter to base? Emitter to base. Emitter to
Yeah.
base. Is it forward bias? Just that diode right there?
okay? Yeah.
Got a negative?
Yeah.
Positive. Forward bias. I forgot another way I've been drawing this. Sorry, I only do this like once a year. Another way to draw it, and this is kind of a cool way too. I forgot. NPN. I had to pull out my drawings.
Why is that cool?
It just makes sense. So in an NPN, all right. So let's see here. If I had a battery, what goes right here? Negative or positive?
Negative.
All right, see, you got it. Positive, negative, positive. All right, positive. All right, so we're going to come up here.
Positive.
Now, you're always going to see some resistors down here. They're called biasing resistors, which means that's how we get the more negative, less negative, more positive, less positive kind of thing going. So if we bring this down over here and we attach this over to here, is this positive in respect to this is the emitter over here? Is the base, this is the base down here, remember? Is the base forward bias in respect to the emitter?
Yes.
Yeah.
So I did draw this correct so far, yes?
Yeah. So far.
Okay, so far. Now we're going to want to do this. I come up over here because my little face is right there, and we'll put a light bulb here. Not an LED because I don't want to make things even worse. And I'm going to come over to here. Okay. Now, this is on the positive side for sure. But, and what I said is this has to be reverse bias, right?
Yeah.
So this has got to be reverse.
Yeah.
So that means that this up here, the N should be
Or negative now.
positive
Oh.
in respect to this.
And we change that by adjusting where it is on the two resistors below the P.
So that's why that becomes a biasing resistor. So now if we look at that and we wanted to put our Simpson meter across these things, which one is the most positive? Not looking at the N or the P, but simply looking at what I've drawn here. Got a bunch of resistors here, biasing resistors, and just a simple light bulb right there. So which side would you consider the positive side and which would be the negative side?
That makes sense.
Yeah. The one with the least amount of voltage.
It's still a little hard to picture, I think. So,
What has less
You're saying,
resistance?
yeah, exactly. Well, that's what
but this light is going to work because we've got a positive this way and a negative over this way. It's flowing this way. It's just the way it's got to be connected. It's reverse biased. They want it reverse biased. So it is reverse biased. Maybe we should do it this way. It is reverse biased. But if we just look at the reverse bias, is it on? I know what I'll do. I'll do it that way. Let me get rid of this and say, yeah, it's reverse bias because we'll leave it at that. What is over here? So this came out this way. We'll just call it this way. I think I can make it more simple. This is
Positive.
positive. This went through the load. Therefore, it's the
Negative.
fine. Is it forward bias or reverse bias? Oh, I just screwed it up. That didn't work. Sorry.
Man.
Thought, wait a minute. I got it. It's going to make sense to you, but no, it doesn't work. That would be forward bias. So, yeah, that's reverse bias. Oh, we did. Oh, shoot. I'm sorry. It's way past break.
The way this is going, we don't need to take a break.
All right.
We don't deserve.